60,000 years ago, our ancestors embarked on the greatest journey in human history, a migration that would eventually populate almost every habitable corner of Earth. The journey that would define humanity's future and shape who we are today. Against all odds, small bands of Homo sapiens left their African homeland and ventured into unknown lands. The world they encountered was harsh and unforgiving, populated by other human species who had left Africa hundreds of thousands of years earlier. Imagine standing at the shores of the Red Sea, the wind carrying salt and promise across the water. Behind you lies the only world your kind has ever known. Ahead, across the narrow strait, an entirely new continent awaits, unexplored, dangerous, yet somehow calling. What compelled these early humans to leave? What challenges did they face as they spread across the globe? And perhaps most intriguingly, whom did they meet along the way? The answers may surprise you. Tonight, we explore the most consequential migration in our species' history, the journey that allowed Homo sapiens to become the last human species standing. A journey filled with adaptation, innovation, and encounters with our evolutionary cousins. Recent genetic evidence has revolutionized our understanding of this migration. DNA extracted from ancient bones tells a story more complex and fascinating than scientists ever imagined. It reveals interbreeding between different human species, once thought impossible. The genetic legacy of these encounters lives on in most people alive today. If your ancestors came from Europe or Asia, you likely carry Neanderthal DNA in your cells. If your heritage is Melanesian or Australian Aboriginal, you may carry genes from the mysterious Denisovans. Some isolated populations may even carry DNA from human species we haven't yet discovered. Fragments of ghost populations detected only through genetic echoes in modern humans. These ancient liaisons challenge our very understanding of what it means to be human. This is not merely academic curiosity. Understanding our origins and how we adapted to diverse environments holds keys to our future. From medical advances to insights about human resilience, our ancient past continues to shape our present and future. The story begins with small bands of humans facing a changing climate in Eastern Africa. Climate records show increasing aridity around 70,000 years ago, pushing some groups toward coastal regions. Here, rich marine resources may have provided the stability needed for population growth. Some researchers suggest these coastal adaptations were crucial. Learning to harvest seafood provided reliable nutrition and possibly supported cognitive development. These skills may have prepared early humans for the challenges that lay ahead. Others point to genetic innovations or cultural developments, improved language, better tools, new social structures. Whatever the catalyst, something remarkable happened. Our species, previously confined to Africa for over 200,000 years, suddenly began to spread. The crossing from Africa to Arabia may have occurred during periods when sea levels were lower. Narrower water gaps would have made the crossing possible, perhaps using simple rafts or even swimming. Multiple exodus events likely occurred, not just a single migration. Tracing this journey requires us to piece together scattered evidence, fossils, stone tools, genetic markers, and climate records. Each discipline provides part of the puzzle. Together, they reveal a remarkable story of human ingenuity and adaptation. As we follow their footsteps tonight, we'll explore questions that have puzzled scientists for generations. How did our ancestors adapt to dramatically different environments? What happened when they encountered other human species? And why did we survive while they vanished? The most profound questions may be philosophical. What does it mean that we once shared the planet with other thinking beings? How might our world be different if they had survived alongside us? What would it mean for our concept of human uniqueness? By the way, have you ever wondered what you might have in common with a Neanderthal? The answers might surprise you. Feel free to share your thoughts in the comments below. Our journey takes us from the scorching deserts of North Africa to the frozen steppes of Ice Age Europe, from the dense forests of Asia to the isolated shores of Australia. Each environment presented unique challenges that shaped our ancestors' bodies, tools, and societies. recent discoveries continue to rewrite the timeline. Human remains in Greece dating to 210,000 years ago suggest earlier migration attempts. Stone tools in northern China push back human presence in East Asia to 2.1 million years ago, though these represent earlier human species. For decades, scientists believed Homo sapiens left Africa around 60,000 years ago in a single wave. New evidence suggests multiple migrations, some perhaps as early as 120,000 years ago. These early ventures may have initially failed, leaving little genetic legacy in today's population. The successful migration, the one that populated the world, likely began around 60,000 years ago. From an initial group perhaps as small as a few hundred individuals, every non-African person today descends from this remarkable journey. Chapter 2. The Last Human Species. The journey we're exploring isn't just ancient history, it's the foundation of our modern world. The migrations that began 60,000 years ago established the basic distribution of human populations we see today. They set in motion genetic and cultural patterns that continue to shape us. Consider this. Every person of non-African descent carries genes from these ancient migrants. Your very existence, the specific combination of traits that make you uniquely you, stems from decisions made by ancestors who chose to venture into the unknown. More remarkably, most people outside Africa carry DNA from other human species entirely. These genetic inheritances aren't just curiosities, they've helped shape our immune systems, our ability to adapt to high altitudes, and potentially even our brain development. Neanderthal genes may influence how your body responds to infections, how your blood clots, and how your skin reacts to sunlight. Denisovan DNA helps Tibetans thrive at high altitudes where oxygen is scarce. Our ancestors' encounters with these other humans continue to affect us today. The stakes of understanding this story extend beyond academic interest. By mapping how humans adapted to diverse environments in the past, we gain insights into our species' capacity for future challenges. Climate change, emerging diseases, even space exploration, all benefit from understanding human adaptability. There's also profound meaning in recognizing we weren't always the only humans. For most of our existence, we shared the planet with other thinking, tool-making, culturally complex beings. This realization challenges our perception of human uniqueness and our place in nature. What if these other human species had survived? Would we have developed technologies together, learned from each other's adaptations, or engaged in devastating conflicts? How would religious traditions, philosophical concepts of humanity, or legal systems accommodate multiple human species? The migration story also reframes how we understand human differences. The physical variations we observe between populations today represent recent adaptations to different environments. Beneath these surface differences, we remain remarkably genetically similar, more so than almost any other mammal species. Our successful spread across the planet required remarkable adaptability. Humans entering new environments faced unfamiliar plants, animals, weather patterns, and diseases. Those who survived passed on traits that helped them thrive in these conditions. Dark skin protected equatorial populations from ultraviolet radiation damage. Lighter skin helped northern populations produce sufficient vitamin D with limited sunlight. Compact body shapes conserved heat in cold climates, while longer limbs dissipated heat in warmer regions. But genetic adaptation alone wasn't enough. What truly set Homo sapiens apart was our capacity for cultural adaptation, developing new tools, techniques, clothing, and social structures to meet environmental challenges. This cultural flexibility may have given us a crucial edge over other human species. Archaeological evidence shows accelerating innovation during this period. More complex stone tools, the first clear evidence of symbolic thinking, and increasingly sophisticated hunting technologies all appear. These developments suggest cognitive or social changes that enhanced our adaptive capacity. Some scientists propose that language reached a critical threshold during this period. Enhanced communication would have allowed for more complex cooperation, knowledge transfer between generations, and abstract planning. These abilities would prove crucial for surviving in unfamiliar environments. Others suggest changes in social organization, larger, more complex groups with specialized roles and extended kinship networks. Such structures could support greater resource sharing, information exchange, and collaborative problem-solving. These social innovations may have been as important as any physical or technological adaptation. The migration also changed Earth itself. As humans spread, large mammal extinctions followed. From woolly mammoths in Europe to giant wombats in Australia, many megafauna disappeared shortly after human arrival, though climate change may have played a contributing role. Human dispersal created the first truly global species of large mammal, capable of affecting ecosystems worldwide. This unprecedented ecological impact foreshadowed our current role as the dominant force shaping Earth's systems. Understanding our ancient impact may help us manage our modern influence more wisely. Perhaps most poignantly, the journey transformed our relationship with other human species. For hundreds of thousands of years, multiple human types had coexisted, adapted, and evolved in separate regions. Our global expansion changed this ancient pattern forever. Within approximately 40,000 years of leaving Africa, Homo sapiens had reached nearly every habitable landmass. And within this same time frame, every other human species had disappeared. The timing suggests these events are connected, though the exact mechanisms remain hotly debated. Did we outcompete other humans for resources? Did diseases spread between populations with devastating effects? Did climate changes favor our adaptations over theirs? Or was there direct conflict between different human groups? The evidence remains incomplete. What we know with certainty is that interbreeding occurred. Genetic evidence shows clear signs of hybridization between Homo sapiens, Neanderthals, Denisovans, and likely other unidentified human species. These encounters were significant enough to leave detectable traces in our DNA today. The implications are profound. Our success as a species wasn't just about outlasting or outcompeting our evolutionary cousins. In some sense, we absorbed them, incorporating their genetic adaptations into our own lineage. We are, in part, the species we replaced. This realization transforms how we understand human uniqueness. Rather than being entirely separate from other human types, we are partially their descendants. The boundaries between human species were more fluid than previously believed. Our evolutionary story is one of both competition and connection. Chapter 3. The Cradle of Humanity. To understand the Great Migration, we must first return to humanity's birthplace, Africa. The continent that nurtured our species for over 200,000 years before the Exodus began. A land of remarkable geographic and climatic diversity that shaped our early development. The earliest fossils recognized as Homo sapiens date to approximately 300,000 years ago in Morocco. This finding surprised scientists who had long believed our species evolved in East Africa. It suggests our origins may be Pan-African, with populations across the continent contributing to our emergence. These early humans weren't quite like us. Their skulls show a mixture of archaic and modern features. Their behavior, as revealed by archaeological remains, lacked the complexity we associate with later populations. They were Homo sapiens anatomically, but not yet behaviorally modern. For over 200,000 years, these early humans remained confined to Africa. During this time, other human species, descendants of earlier migrations out of Africa, had already spread across Eurasia. Homo erectus reached Java by 1.8 million years ago. Neanderthals dominated Europe and the Middle East. Africa during this period underwent dramatic climate shifts. Ice ages to the north caused periods of extreme drought, followed by wetter intervals. These fluctuations created environmental pressures that may have driven human adaptation and innovation. Survival required flexibility and new strategies. Between 150,000 and 70,000 years ago, something remarkable happened. Archaeological sites begin showing signs of more complex behavior, standardized tool production, long-distance trade networks, and the first clear evidence of symbolic thinking. Our ancestors were becoming more like modern humans. Red ochre pigment processed and stored in abalone shells appears in South African caves dating to 100,000 years ago. Shell beads used as personal ornaments emerge around the same time. These findings suggest the development of symbolic thought and possibly spiritual beliefs. Stone tool technology became more sophisticated. Carefully shaped projectile points, blades, and specialized tools for processing various materials appear. These advances suggest improved cognitive abilities and perhaps enhanced communication, allowing complex knowledge transfer between generations. Some researchers believe these behavioral changes reflect genetic mutations affecting brain function. Others argue they represent cultural innovations transmitted through increasingly sophisticated language and social learning. The debate continues, but the evidence for behavioral transformation is clear. Genetic studies suggest human populations in Africa experienced bottlenecks around 170,000 years ago. Climate records show periods of extreme aridity that may have reduced human populations to just a few thousand individuals. These challenging conditions may have accelerated adaptation and innovation. The Toba supervolcano eruption around 74,000 years ago may have further stressed human populations. This massive eruption in Indonesia caused global cooling and environmental disruption. Some researchers believe it reduced human populations to near extinction levels, though this remains contested. Whatever the cause, genetic evidence indicates all non-African humans today descend from a small population that existed around this time. Perhaps just a few hundred or thousand individuals gave rise to the billions of people who would eventually populate the rest of the world. By 70,000 years ago, human populations in Eastern Africa showed signs of significant cultural complexity. Stone tools were being traded over long distances. Marine resources were being systematically exploited. Social networks appear to have expanded beyond immediate family groups. These developments may have prepared humans for the challenges of migration. More complex social networks could support information sharing about distant lands. Improved tools and hunting techniques allowed adaptation to unfamiliar environments. Cultural innovations provided flexibility beyond genetic adaptation. Coastal adaptations may have been particularly important. Shell middens, ancient trash heaps containing seafood remains, show humans were effectively exploiting marine resources by this time. These predictable food sources could have supported growing populations and provided stable nutrition for expanding groups. Following coastlines may have been a key migration strategy. Marine resources would have provided reliable food, even in unfamiliar territories. Coastal routes might have allowed humans to spread rapidly without requiring immediate adaptation to inland environments. This coastal highway hypothesis remains influential. Climate records show that around 60,000 years ago, conditions briefly improved. Increased rainfall in northeastern Africa and the Arabian Peninsula created green corridors through what are now deserts. These temporary pathways may have facilitated movement out of Africa. Sea levels were also significantly lower during this period due to global ice buildup. The Bab el-Mandeb Strait between Africa and Arabia may have narrowed to just a few kilometers. This relatively small water crossing could have been navigated with simple rafts or even by swimming. Multiple possible exit routes existed. The northern route through the Sinai Peninsula and Levant, the southern route across the Red Sea to Arabia. Evidence suggests both may have been used, though the southern route appears to have led to the most successful dispersal. The humans who left Africa were physically similar to modern humans, but lived in much smaller groups. They likely traveled in extended family bands of 20 to 50 individuals. These small, mobile groups could adapt quickly to new circumstances, but were vulnerable to environmental challenges. Their worldview remains unknowable, but we can speculate based on later hunter-gatherer societies. They likely perceived themselves as part of nature, not separate from it. Their spirituality may have centered on animistic beliefs, seeing consciousness in animals, plants, and natural features. What motivated them to leave their homeland? We can never know with certainty. Perhaps population pressure as groups grew. Maybe climate shifts making familiar territories less productive, or simply human curiosity, the same impulse that eventually took us to the moon. Whatever drove them, the consequences of their journey would be profound. These small bands of pioneers carried the genetic and cultural foundations of all non-African humanity. Their decisions, adaptations, and encounters would shape the future of our species in ways they could never imagine. Chapter 4. First Steps into a Wider World. The earliest evidence of Homo sapiens outside Africa comes from the Levant, modern-day Israel and surrounding regions. Fossils discovered at Skul and Kafze caves date to between 120,000 to 90,000 years ago. These findings suggest earlier migration attempts predating the main exodus. These early ventures appear to have been limited in scope and success. The humans at Skul and Kafze seem to have been temporary visitors rather than permanent colonizers. Their genetic legacy in modern populations appears minimal. They may represent failed migration attempts during temporary climate improvements. The successful migration, the one that populated the world, likely began around 60,000 years ago. Archaeological evidence shows human presence in Arabia by this time. Stone tools found at Jebel Fire in the UAE date to approximately 125,000 years ago, though their makers remain debated. Recent discoveries at Al-Wusta in Saudi Arabia strengthen the case for early human presence in Arabia. A human finger bone directly dated to 88,000 years ago was found alongside stone tools and animal remains. This finding confirms humans had at least temporarily moved beyond Africa's borders. The Arabian Peninsula looked dramatically different during these periods. Instead of today's harsh deserts, much of the region featured grasslands, lakes, and rivers. These savanna-like environments would have been familiar to humans, adapted to East African ecosystems. Game animals similar to those in Africa roamed these landscapes. Climate records show these favorable conditions fluctuated dramatically. Wet periods allowing human expansion alternated with extreme aridity that would have made much of Arabia uninhabitable. These fluctuations may explain why early migrations didn't lead to permanent settlement. The first unequivocal evidence of the successful migration comes from Australia. Archaeological sites in northern Australia date human arrival to at least 65,000 years ago. This remarkable finding indicates humans had traversed the entire southern coast of Asia by this time. Reaching Australia required multiple sea crossings, including one of at least 90 kilometers, even during the lowest sea levels. This journey implies maritime capabilities far beyond simple rafts. Early Australians must have possessed boats capable of supporting multiple people over significant distances. How did humans spread so rapidly from Arabia to Australia? The coastal migration hypothesis offers one explanation. Following shorelines would provide reliable food sources and familiar environments. Marine resources could sustain populations even as they moved through otherwise unfamiliar territories. Genetic evidence supports the coastal route scenario. DNA from indigenous populations across southern Asia shows patterns consistent with rapid movement along coastlines. The highest genetic diversity appears in populations nearest to Africa, decreasing with distance. Exactly what we'd expect from serial migration. The coastal regions these early humans followed now lie underwater. Sea levels were 120 meters lower during the Ice Age, exposing vast continental shelves. Many archaeological sites from this critical period are likely submerged beneath the ocean. This underwater heritage presents enormous challenges for researchers. Despite these difficulties, evidence of early human presence continues to emerge. In India, sophisticated stone tools dating to 80,000, 65,000 years ago have been discovered. In Southeast Asia, comparable technologies appear by 65,000 years ago. These findings trace the path of migration eastward. The humans who made this journey encountered environments increasingly different from their African homeland. Tropical rainforests in Southeast Asia presented new plants, animals, and challenges. Seasonal monsoons created cyclical patterns of abundance and scarcity. New diseases tested immune systems evolved in Africa. Adaptation occurred through both biological and cultural means. Genetic changes helped populations adjust to new environments over generations. Cultural innovations allowed for more immediate responses, new hunting techniques, plant processing methods, and shelter construction. As our ancestors moved eastward, they eventually encountered other human species already established in these regions, the descendants of much earlier migrations out of Africa. Species like Homo erectus had occupied parts of Asia for over 1 million years. These encounters would prove momentous. In the Denisova cave in Siberia's Altai Mountains, archaeologists discovered something extraordinary. A small finger bone yielded DNA, unlike that of any known human. This new human species, named Denisovans after the cave, had diverged from our lineage approximately 600,000 years ago. Further genetic studies revealed something even more remarkable. Modern Melanesians and Australian Aboriginals carry up to 6% Denisovan DNA. This genetic signature proves interbreeding occurred between our ancestors and these mysterious humans. A profound encounter preserved in our genetic code. Neanderthals tell a similar story. Once depicted as brutish cave dwellers, we now know they had complex culture, buried their dead, created art, and possessed language capabilities. They had adapted to European and Western Asian environments over hundreds of thousands of years. When our ancestors encountered Neanderthals, they too interbred. All non-African humans today carry approximately 1–4% Neanderthal DNA in their genomes. These genetic contributions may have helped our ancestors adapt more quickly to Eurasian environments. Beneficial Neanderthal genes were selectively retained. The implications are profound. We did not simply replace other human species, we partially merged with them. The boundaries between human types were more fluid than previously believed. Our evolutionary story includes both competition and connection. The timeline of these encounters presents a mystery. Genetic evidence indicates Neanderthal sapiens interbreeding occurred approximately 50,000 to 60,000 years ago. Yet humans had already reached Australia by 65,000 years ago. How do we reconcile these apparently contradictory findings? One possibility is multiple migration waves. Perhaps the first migrants followed coastal routes rapidly to Southeast Asia and Australia. Later waves moved more slowly through inland territories where Neanderthals lived. The genetic evidence remains complex and sometimes contradictory. The ultimate fate of these other human species presents another mystery. Neanderthals disappear from the fossil record approximately 40,000 years ago. Denisovans' extinction date remains unknown due to limited fossils, but they too vanished. What role did our ancestors play in their disappearance? Did competition for resources drive them to extinction? Did diseases spread between populations with devastating effects? Was there direct conflict? Or did they simply assimilate into the growing Homo sapiens population through interbreeding? The evidence remains insufficient for definitive answers. What we do know is that within approximately 30,000 years of leaving Africa, Homo sapiens had reached every habitable continent except the Americas. And within this same time frame, every other human species had disappeared or been absorbed. We had become the last humans standing, but the story takes an even more mysterious turn. Genetic studies of isolated populations have detected DNA segments that match neither Neanderthals, Denisovans, nor Homo sapiens. These genetic ghosts suggest encounters with human species we haven't yet found in the fossil record. In 2019, a remarkable discovery added another layer to this complex story. On the Tibetan Plateau, a jawbone previously thought to be Neanderthal yielded Denisovan DNA. This first Denisovan fossil found outside Siberia revealed they had adapted to high-altitude environments long before humans arrived. Even more intriguing, the genetic adaptation that helps modern Tibetans survive at high altitudes came from Denisovans. When our ancestors reached the Tibetan Plateau, they acquired this crucial adaptation through interbreeding. Ancient innovation became modern survival through genetic exchange. As we've traced the first steps of humanity's Great Migration, evidence points to a far more complex story than scientists once imagined. Not a simple tale of conquest and replacement, but one of adaptation, interaction, and even intimacy between different human kinds. What awaits us as we follow this journey further? How did early humans survive the extremes of Ice Age Europe? What innovations allowed them to thrive in environments no African-evolved species should have been able to endure? And what happened when they reached the Americas? The most profound questions may lie in the genetic and cultural legacy of these ancient journeys. How much of who we are today, our physical traits, disease resistances, cognitive tendencies, stems from these ancient migrations and encounters? The answers continue to emerge, reshaping our understanding of ourselves. Recent studies have found that Neanderthal DNA influences traits as diverse as skin tone, hair color, sleeping patterns, mood disorders, and immune response. Some Neanderthal genes increase risk of depression and addiction. Others offered vital protection against pathogens in the new environments our ancestors encountered. Perhaps most remarkably, one specific Neanderthal gene variant affects how our cells interact with RNA viruses. This includes coronaviruses and influenza. The very mechanisms helping some people fight COVID-19 may have entered our lineage through interbreeding tens of thousands of years ago. As we prepare to follow our ancestors deeper into their global journey, a startling possibility emerges. What if we are not merely the descendants of those who left Africa 60,000 years ago? What if we are, in fact, a hybrid species, a living mosaic of multiple human types who once walked the earth? Chapter 5. When evidence challenges history. As we continue following the great human migration, certain findings challenge the neat narrative scientists once constructed. Unexpected discoveries have emerged that don't fit the established timeline. These anomalies don't invalidate the migration story, but suggest it was far more complex than initially believed. Consider the mystery of Australia's settlement. Archaeological evidence places humans in northern Australia by at least 65,000 years ago. Yet genetic studies of Aboriginal Australians suggest their ancestors diverged from other populations around 72,000 years ago, before the presumed main exodus from Africa. This contradictory evidence creates a puzzle. How could humans reach Australia before the main out-of-Africa migration? One possibility is that multiple successful migrations occurred, not just a single exodus. The traditional narrative of a single departure around 60,000 years ago may be oversimplified. Recent discoveries in China further complicate the picture. In 2015, researchers reported finding 47 human teeth in Fuyan Cave, dating to between 80,000 and 120,000 years ago. If confirmed, this would place Homo sapiens in southern China long before they were thought to have left Africa. Similarly, stone tools discovered in the Arabian Peninsula at sites like Jebel Faya date to 125,000 years ago. Their style suggests they were made by Homo sapiens rather than other human species. This evidence points to human presence in Arabia during an earlier climatic window when conditions were favorable. These findings suggest a more complex migration pattern, perhaps multiple waves of expansion during favorable climate periods, with many early attempts failing as conditions deteriorated. The successful migration around 60,000 years ago may have been preceded by several unsuccessful ventures. Another mystery emerges in the Levant. Human remains from School and Kafsa caves date to 90,000 to 120,000 years ago. Yet Neanderthals occupied the same region from 70,000 to 50,000 years ago. This suggests an early human expansion followed by a retreat, with Neanderthals reclaiming the territory. What caused this apparent human retreat from the Levant? Climate change may have played a role, as the region became drier and less hospitable. Or perhaps these early migrants lacked cultural or biological adaptations necessary for permanent settlement. Their disappearance remains unexplained. The timing of human arrival in different regions creates further contradictions. Genetic evidence suggests the main migration from Africa occurred around 60,000 years ago. Yet archaeological findings place humans in Australia by 65,000 years ago. This timeline seems impossibly compressed. To reach Australia from Africa within 5,000 years would require remarkable speed. Migrants would need to traverse the Arabian Peninsula, Indian subcontinent, Southeast Asia, and make multiple sea crossings. All while adapting to new environments, developing boat technology, and establishing sustainable populations along the way. Some researchers suggest these timeline contradictions indicate our dating methods may have flaws. Others propose that early migrations were more rapid than previously believed, possibly following coastlines where marine resources allowed for quick movement without requiring complex adaptations to inland environments. The genetics of Melanesian and Australian Aboriginal populations present another anomaly. These groups carry significant Denisovan DNA, up to 6% of their genome. Yet, the only confirmed Denisovan fossils come from Siberia and Tibet, thousands of miles from the presumed interbreeding location. This geographic disconnect suggests Denisovans were far more widespread than fossil evidence indicates. They likely inhabited much of East and Southeast Asia. Our understanding of their range and history remains severely limited by the scarcity of fossils. Most of what we know comes from genetic evidence. If you're feeling a bit uncertain about where all these anomalies fit, you're not alone. I'd be curious to hear which of these contradictions you find most intriguing. Let us know in the comments below. Even the Neanderthal interbreeding story contains puzzles. Genetic evidence indicates Neanderthal DNA entered our lineage approximately 50,000, 60,000 years ago. Yet humans had already reached Australia by then. How could Neanderthal genes spread to populations that had already migrated beyond Neanderthal territories? One explanation involves multiple migration waves and subsequent genetic mixing. Perhaps earlier migrants left Africa without encountering Neanderthals, while later groups interbred with them. These later groups could have then spread and mixed with earlier migrants, distributing Neanderthal DNA widely. The diverse physical adaptations of human populations complicate matters further. Features like skin color, body proportions, and facial characteristics vary significantly between populations. These adaptations to different environments would require considerable time to develop through natural selection. Could such diverse adaptations emerge in just 60,000 years? Some geneticists argue this time frame is insufficient for such widespread physical differentiation. Others suggest selection pressures in extreme environments could accelerate adaptive changes, especially in small isolated populations. Recent studies of ancient DNA have identified genetic signatures of ghost populations, human groups that left no fossil record but whose genetic contributions persist in modern people. These findings suggest interbreeding with unknown human types occurred repeatedly during our dispersal across the globe. In 2019, researchers identified a previously unknown human population that contributed to West African genomes. This ghost population diverged from our lineage before Neanderthals, but interbred with African humans within the past 50,000 years. Their existence was detected solely through genetic analysis. Similarly, genetic studies of indigenous Americans have found DNA segments that match neither Neanderthal nor Denisovan patterns. These segments likely come from yet another unknown human species that interbred with the ancestors of Native Americans, a phantom population detected only through its genetic echoes. These discoveries suggest our evolutionary tree is not a simple branching pattern, but a complex network of interconnected populations. Different human types separated, adapted to various environments, and later reconnected through interbreeding. Our ancestry is less a tree and more a tangled web. The cognitive leap that enabled modern human behavior presents another mystery. Archaeological evidence shows a dramatic increase in technological and cultural complexity around 70,000, 50,000 years ago. This cultural revolution coincides with the successful migration out of Africa. What triggered this cognitive transformation? Some researchers propose genetic mutations affecting brain function. Others suggest cultural innovations reached a critical threshold, allowing more complex knowledge transmission. The debate continues, with implications for understanding human uniqueness. Intriguingly, some Neanderthal populations show similar signs of cultural advancement during this period. Cave art, shell jewelry, and complex tools appear in Neanderthal contexts shortly before their disappearance. Did they develop these independently, or was there cultural exchange with incoming Homo sapiens? The timing of Neanderthal extinction creates another contradictory puzzle. In some regions, Neanderthals disappeared shortly after Homo sapiens arrived. In others, the two species apparently coexisted for thousands of years. This inconsistent pattern defies simple explanations of replacement or competition. In Iberia, modern Spain and Portugal, Neanderthals persisted until approximately 40,000 years ago, nearly 10,000 years after humans arrived in Europe. This long coexistence challenges the notion that direct competition with humans quickly drove Neanderthals to extinction. The Denisovans present an even greater mystery. Despite their significant genetic contribution to some modern populations, we have remarkably few Denisovan fossils. Just a finger bone, a few teeth, and a jawbone. Their physical appearance, cultural capabilities, and exact range remain largely unknown. How could a population that left such a substantial genetic legacy remain so invisible in the fossil record? Were their population numbers always small? Did they practice burial customs that reduced fossil preservation? Or have we simply been looking in the wrong places? The climatic conditions during this migration period add another layer of complexity. The world was in the grip of the last ice age, with dramatically different coastlines, vegetation patterns, and animal distributions. Sea levels were up to 120 meters lower than today. These ice age conditions created both barriers and bridges. Expanded glaciers blocked northern routes, while exposed land bridges opened new pathways. Reconstructing these ancient landscapes is essential for understanding migration routes, yet remains challenging despite advanced climate modeling. Perhaps the most significant contradiction concerns the Americas. The traditional narrative held that humans reached North America around 13,000 years ago, crossing the Bering Land Bridge and moving south as glaciers retreated. This Clovis first model seemed well established. Recent discoveries have thoroughly dismantled this timeline. Sites like Monte Verde in Chile show human presence by 18,500 years ago. Chiquihuite Cave in Mexico has evidence suggesting human activity as early as 30,000 years ago. The peopling of the Americas was earlier and more complex than previously believed. These contradictions and anomalies don't invalidate the Out of Africa story. Rather, they reveal a far more intricate narrative of human dispersal, multiple migrations, false starts, retreats, and complex interactions between different human populations. The simple story is giving way to a richer understanding. As our journey continues, we'll explore how cultural memories preserved in myths and legends might contain echoes of these ancient migrations and encounters. And we'll examine how indigenous knowledge sometimes preserved information that science is only now rediscovering. The past speaks to us in many voices. Chapter 6: Echoes in Myth and Legend. Throughout the world, indigenous cultures preserve stories that seem to echo the Great Migration. Creation myths, ancestral journeys, and tales of strange encounters may contain kernels of historical truth. While we must approach such evidence cautiously, these narratives sometimes align remarkably well with scientific findings. Aboriginal Australian Dreamtime stories describe the arrival of their ancestors from across the sea. These narratives speak of a time when sea levels were lower and the journey required crossing water. Such details align with archaeological evidence of migration during the Ice Age, when sea levels were indeed lower. Some Aboriginal stories describe physical features of the landscape that have been underwater for thousands of years. Oral traditions recall coastal plains now submerged beneath the ocean. These geographical memories would have been passed down for at least 7,000 years since sea levels stabilized. In one remarkable example, Aboriginal stories describe a coastal volcano and the dramatic tsunami it caused. Geological evidence confirms such an eruption occurred approximately 7,000 years ago. This suggests accurate oral transmission of eyewitness accounts across hundreds of generations. If some Aboriginal traditions accurately preserved memories from 7,000 years ago, might others reach back even further? Some anthropologists suggest certain Dreamtime stories could contain memories of encounters with other human species. Tales of strange, hairy people who could not make fire might reference such meetings. Similar stories appear in folklore worldwide, from the Orang Pendek of Indonesia to the Almas of Central Asia, from the Yeti of the Himalayas to the Sasquatch of North America. Many cultures describe encounters with human-like beings distinct from themselves. Skeptics rightfully note that these legends could simply reflect human imagination or misidentification of known animals. Yet the persistence of such narratives across cultures that had no contact with each other remains intriguing. Could some reflect ancestral memories of encounters with other human species? Genetic evidence confirms our ancestors did meet and interbreed with other human types. These encounters must have been memorable, even transformative, for the small bands of Homo sapiens venturing into new territories. It would be surprising if such profound experiences left no cultural traces. Indigenous peoples of the Andaman Islands in the Indian Ocean provide another example. Genetic studies show they descended from some of the earliest migrations out of Africa. Their oral traditions speak of being the first inhabitants of their islands, arriving before other peoples. The Andamanese had no prior contact with modern science, yet their traditional knowledge aligned with genetic findings. Their distinctive physical traits, dark skin, short stature, and tightly curled hair, also suggest long isolation and adaptation to their tropical island environment. Across Siberia and the far north, indigenous peoples preserve stories of an ancient homeland far to the south. Many describe ancestral migrations northward as climate improved, following game animals into previously uninhabitable terrain. This pattern aligns with archaeological evidence of human expansion after the last glacial maximum. Native American origin stories often describe journeys from elsewhere, crossing water, emerging from underground, or descending from the sky. While these narratives use symbolic language, many contain geographical references to migration routes, consistent with archaeological findings. The cultural memory of movement persists. The Navajo speak of emerging into this world after dwelling in 3 previous worlds below. Their migration stories describe a journey from the north, moving southward in stages. These directional elements align with archaeological evidence of migration routes into the American Southwest. Beyond myths, there are puzzling archaeological discoveries that don't fit neatly into the established narrative. These out-of-place findings don't necessarily contradict the broad migration story, but suggest our understanding remains incomplete. They hint at capabilities or connections not previously recognized. Stone tools found at the Cerruti Mastodon site in California were initially dated to approximately 130,000 years ago, long before humans were thought to have reached the Americas. This controversial finding remains disputed, with many archaeologists questioning either the dating or the human origin of the markings. In Brazil's Serra da Capivara National Park, rock art and archaeological remains have been dated to over 20,000 years ago. These findings challenge the traditional timeline for human arrival in South America. If verified, they would require completely rethinking migration routes into the Americas. I'm curious, do you know any local legends from your region about ancient peoples or mysterious beings? The comments section is a perfect place to share these cultural stories that might contain echoes of our distant past. On the other side of the world, the indigenous Ainu people of northern Japan present another anomaly. Physically distinct from other East Asian populations with lighter skin and more body hair, they were long considered an enigmatic outlier. Genetic studies now suggest they descend from some of the earliest migrations into East Asia. The Ainu maintained distinctive cultural practices and a hunter-gatherer lifestyle into modern times. Their traditional beliefs, featuring elaborate bear ceremonies and nature worship, may preserve elements from the earliest human cultures in northern Asia. Their existence challenges simplified views of Asian prehistory. In Europe, cave art provides another form of cultural memory. The magnificent paintings at Chauvet, Lascaux, and Altamira depict Ice Age animals with remarkable accuracy. Created between 40,000 and 15,000 years ago, they reveal sophisticated artistic traditions and deep knowledge of animal behavior. Some researchers propose these cave paintings weren't merely art, but served as information storage systems. They may have recorded seasonal animal migrations, hunting techniques, or spiritual knowledge. If so, they represent a form of communication that preserved vital information across generations. Certain cave paintings feature strange human-animal hybrid figures or handprints with missing fingers. These mysterious elements have been variously interpreted as shamanic imagery, depictions of spiritual transformation, or representations of human-animal relationships. Their meanings remain open to interpretation. The Venus figurines, small female statues with exaggerated sexual characteristics, present another mystery. Found across Europe and Siberia from 38,000 to 14,000 years ago, they share remarkable similarities despite being created by widely separated cultures. This suggests common symbolic meanings or long-distance cultural connections. In some cases, archaeological evidence directly contradicts earlier assumptions about human capabilities. The settlement of Australia, for instance, required substantial maritime technology to cross open water gaps of at least 90 kilometers. Early humans were clearly more capable seafarers than previously believed. Similarly, evidence of human habitation on islands like Flores in Indonesia dates to over 1 million years ago. This indicates that even earlier human species like Homo erectus possessed basic seafaring abilities. Our ancestors' maritime capabilities have been consistently underestimated. The discovery of Homo floresiensis, the so-called hobbits, on Flores, added another layer to this mystery. This small-bodied human species existed until approximately 50,000 years ago. Their presence on an isolated island raises questions about how they arrived and what happened when Homo sapiens encountered them. Genetic evidence suggests our ancestors did meet Homo floresiensis. Indigenous populations in the region carry small amounts of DNA that matches neither Neanderthal nor Denisovan patterns. This genetic signature may come from interbreeding with floresiensis or another unknown human species in Southeast Asia. The sophisticated capabilities of early humans appear in other archaeological contexts. At Blombos Cave in South Africa, researchers found evidence of ochre processing, shell bead jewelry, and geometric engravings dating to 100,000 to 70,000 years ago. These findings demonstrate symbolic thinking long before the Great Migration. Even more remarkably, recent discoveries at Pinnacle Point in South Africa suggest humans were heat-treating stone to improve tool-making quality by 164,000 years ago. This complex process requires understanding how materials transform under controlled heating. It demonstrates sophisticated technological knowledge. Marine resources appear to have played a crucial role in human cognitive development. Archaeological sites along the South African coast show systematic exploitation of seafood by 110,000 years ago. The omega-3 fatty acids in these foods support brain development and may have contributed to cognitive advances. The timing of artistic and technological innovations shows puzzling patterns. In some regions, sophisticated technologies appear suddenly without clear precursors. In others, similar innovations seem to develop independently in widely separated locations. These patterns suggest either rapid cultural transmission or parallel innovation. Language development remains perhaps the greatest mystery. With no direct archaeological evidence of speech, researchers must rely on indirect clues like brain structure, symbolic behavior, and technological complexity. When humans developed fully modern language capabilities remains hotly debated. Some linguists propose that all modern languages descend from a common ancestral language spoken in Africa before the Great Migration. This hypothetical proto-human language would have been the speech of the migrants who populated the world. Traces of it might persist in certain grammatical structures or sound patterns. Other researchers suggest language developed gradually, with fully modern capabilities, emerging only after populations had already dispersed. This would explain the tremendous diversity of language families worldwide. The absence of a single ancestral language family would reflect independent development in separated populations. Cultural practices preserved in isolated communities sometimes provide windows into ancient ways of life. The San people of southern Africa, genetically among the oldest distinct human populations, maintained hunter-gatherer lifestyles into modern times. Their techniques for reading animal tracks, finding water, and using medicinal plants represent knowledge accumulated over tens of thousands of years. Similarly, traditional ecological knowledge preserved by indigenous groups often demonstrates sophisticated understanding of local environments. This knowledge frequently aligns with scientific findings, despite developing through entirely different methodologies. It represents another form of cultural memory, preserving ancient wisdom. As we piece together these diverse lines of evidence, genetic, archaeological, climatological, and cultural, a more nuanced picture of the Great Migration emerges. Not a simple linear spread of a single population, but a complex tapestry of movements, encounters, adaptations, and exchanges that ultimately transformed our species. Chapter 7. The Last Among Many. As we deepen our exploration of humanity's great journey, the stakes of this story come into sharper focus. Understanding our origins isn't merely academic curiosity. It fundamentally reshapes how we understand ourselves and our relationship with each other and the planet. The implications extend from medicine to philosophy. For most of human history, we believed our species was unique and separate from nature. Sacred texts and origin myths described special creation events that set humans apart. Scientific evidence now tells a different story. We emerged gradually through evolutionary processes and once shared the planet with other thinking beings. This realization profoundly challenges traditional notions of human uniqueness. We were never alone. For most of our existence as a species, multiple types of humans walked the Earth simultaneously. Each adapted to different environments, developed distinct cultures, and possessed unique capabilities. The Neanderthals had larger brains than us, with expanded visual cortices that may have given them superior night vision. They survived in Ice Age Europe for hundreds of thousands of years, enduring conditions that would challenge modern humans, even with advanced technology. Their extinction represents an incalculable loss of knowledge and perspective. Denisovans adapted to the oxygen-poor environments of the Tibetan Plateau long before our ancestors attempted high-altitude living. Their genetic adaptations for hypoxia tolerance now help modern Tibetans survive at elevations where lowlanders struggle to breathe. Their legacy lives on in human populations across Asia and Oceania. Homo floresiensis, the hobbits of Indonesia, evolved a remarkably small body size and brain while maintaining complex tool-making abilities. They demonstrate that large brains aren't necessarily required for sophisticated behavior. Their existence challenges fundamental assumptions about human cognition. As recently as 50,000 years ago, at least 5 human species inhabited the planet simultaneously. Homo sapiens, Neanderthals, Denisovans, Homo floresiensis, and likely others we haven't yet discovered. Each represented a unique evolutionary experiment, a different way of being human. Today, only one remains. The diversity of human types that once existed has been reduced to a single species. While we maintain considerable genetic and cultural diversity within our species, we've lost the true human diversity that once existed. We are the last humans standing. This realization raises profound questions about our relationship with these lost cousins. Were we responsible for their disappearance? Did competition, conflict, or transmitted diseases drive them to extinction? Or did climate changes and demographic accidents determine their fate independently of our actions? The evidence remains inconclusive, but the timing is suggestive. Within approximately 30,000 years of our species expanding beyond Africa, every other human species had vanished. This pattern implies some causal relationship, though the specific mechanisms remain debated. If our ancestors did contribute to the extinction of other human types, what moral weight should we attach to this ancient history? These events occurred long before written records or modern ethical frameworks, yet they resulted in the loss of unique cognitive perspectives and cultural possibilities that can never be recovered. Imagine a world where multiple human species coexisted into the present. How would our religions, philosophies, and legal systems accommodate such diversity? Would we recognize equal rights and dignity across different human types? Or would our tribalistic tendencies lead to hierarchies and discrimination? These questions aren't merely hypothetical. They speak directly to how we conceptualize humanity and human rights. Our current ethical frameworks assume a single human species. How robust are these frameworks when confronted with the reality that human diversity once meant something far more profound than the variations we see today? If you could speak with a Neanderthal or Denisovan, what would you ask them? What perspectives might they offer on the world that would differ from our own? I'd love to hear your thoughts in the comments. The medical stakes are equally significant. Understanding our evolutionary history and genetic inheritance from other human species directly impacts health research. Neanderthal and Denisovan genes influence modern humans' immune responses, metabolic processes, and disease susceptibilities. During the COVID-19 pandemic, researchers discovered that a gene variant affecting how severely people experience the disease came from Neanderthals. This ancient DNA segment increased risk of severe COVID-19 in some populations, while potentially offering protection against other pathogens. Our extinct cousins continue to influence our health. Other Neanderthal genes affect how modern humans' immune systems respond to various infections. Some influence blood clotting mechanisms and wound healing. Still others impact skin and hair characteristics, potentially helping populations adapt to different climates and UV exposure levels. These ancient adaptations remain relevant today. As we develop precision medicine tailored to individual genetic profiles, understanding these archaic genetic contributions becomes increasingly important. Treatments that work for one population may fail in another due to differences in evolutionary history. Our medical future depends partly on understanding our evolutionary past. Beyond medicine, there are ecological stakes to this story. As our ancestors spread across the globe, they transformed environments through hunting practices, fire use, and eventually agriculture. These impacts began long before the Industrial Revolution and continue accelerating today. The migration coincided with extinctions of large mammals across multiple continents. From woolly mammoths in Europe to giant wombats in Australia, megafauna disappeared shortly after human arrival. While climate change contributed, human hunting likely delivered the final blow to many species already stressed by environmental changes. This pattern suggests our species has been altering ecosystems for tens of thousands of years. We didn't suddenly become a force of nature in recent centuries. Rather, our environmental impact has deep roots in our evolutionary history. Understanding this longer timeline provides context for addressing current ecological challenges. If our ancestors contributed to ecological transformations and extinctions of other species, including other human species, what responsibilities do we bear today? Does this evolutionary history of disruption suggest we should be especially cautious about our current impacts? Or does it normalize environmental transformation as inherent to human existence? There are also profound implications for how we understand human potential and limitations. The Great Migration demonstrates remarkable adaptability. Our ancestors successfully colonized environments ranging from Arctic tundra to tropical rainforests, from high mountains to coastal wetlands. This adaptability stemmed from both biological and cultural innovations. Genetic changes helped populations adjust to different diets, disease exposures, and climate conditions. Cultural innovations allowed much more rapid adaptation through technology, knowledge transmission, and social organization. Together, these mechanisms enabled unprecedented ecological flexibility. Understanding this dual inheritance, genetic and cultural, is crucial for addressing contemporary challenges. Climate change, emerging diseases, food security, and other global issues will require both technological solutions and biological resilience. Our evolutionary history suggests we possess both, though success is never guaranteed. Perhaps most significantly, the migration story reveals that human success came not from isolation and purity, but from connection and exchange. Our ancestors didn't merely outcompete other human species, they interbred with them, incorporating beneficial adaptations into our lineage. Genetic diversity became a strength, not a weakness. Modern humans outside Africa carry 1 to 4% Neanderthal DNA. Indigenous Melanesians and Australian Aboriginals have up to 6% Denisovan ancestry. Some African populations carry DNA from yet other archaic human groups. We are all, to varying degrees, hybrids, living mosaics of different human lineages. Modern humans outside Africa carry 1 to 4% Neanderthal DNA. Indigenous Melanesians and Australian Aboriginals have up to 6% Denisovan ancestry. Some African populations carry DNA from yet other archaic human groups. We are all, to varying degrees, hybrids, living mosaics of different human lineages. This genetic reality contradicts racist ideologies that have historically sought pure lineages or superior populations. The actual story of human evolution involves continuous mixing, with beneficial adaptations spreading between populations. Genetic exchange, not isolation, characterizes our evolutionary success. As we face global challenges requiring unprecedented cooperation, this understanding becomes increasingly valuable. Our species' greatest strength has always been our ability to adapt through both biological and cultural means. And adaptation often comes through connection, exchange, and diversity, rather than separation and homogeneity. The timeline of our story contains another crucial insight. For approximately 200,000 years, Homo sapiens remained confined to Africa with limited technological innovation and population growth. Then, within approximately 50,000 years after beginning the Great Migration, we developed agriculture, cities, writing, and eventually industrial civilization. This accelerating pace of innovation following the migration suggests something profound about human development. Perhaps the challenges of new environments stimulated cognitive and cultural evolution. Perhaps encounters with other human species sparked new ideas and approaches. Perhaps the migration itself selected for adaptability and innovation. Whatever the mechanism, the evidence suggests that confronting new challenges and engaging with difference drove human development. Not comfort and stability, but novelty and adversity sparked our most significant advances. This pattern may hold important lessons for our future. As we continue piecing together humanity's journey, new discoveries continuously reshape our understanding. In 2019, researchers identified human footprints in New Mexico dating to approximately 23,000 years ago, challenging established timelines for the peopling of the Americas. Our story remains dynamic, with each finding potentially rewriting major chapters. DNA analysis techniques continue advancing rapidly. Scientists can now recover and analyze genetic material from increasingly ancient and degraded specimens. Just a few years ago, extracting DNA from 100,000-year-old bones seemed impossible. Today, it's becoming routine. Tomorrow may bring insights from even older remains. Most excitingly, vast regions with potential archaeological significance remain unexplored. The submerged continental shelves that formed coastlines during the Ice Age, remote mountain ranges and deep caves, the dense rainforests of the tropics. These environments may hold crucial evidence of human migrations and encounters. As we stand at this moment of unprecedented knowledge about our origins, we face a pivotal question. What will we do with this understanding? How will recognizing our shared ancestry and hybrid nature influence our future decisions? Will this knowledge bring us together or create new divisions? For most of recorded history, humans divided themselves by tribe, nation, race, and religion. We imagined fundamental differences between groups, often using these perceived differences to justify exploitation and violence. The scientific evidence now thoroughly contradicts these divisive narratives. We now know that all living humans share ancestors who lived just a few thousand years ago. That genetic diversity within traditional racial groups exceeds differences between them. that beneficial adaptations have spread between populations continuously throughout our evolution, we are far more connected than separated. Yet this scientific understanding competes with powerful social and political forces that continue emphasizing difference and division. Our evolutionary legacy includes both cooperation within groups and competition between them. Both tendencies remain active in our psychology and societies, which will prevail in shaping our future. As we continue our exploration of the Great Migration, a profound truth emerges. We are the last survivors of a once diverse family of human species, the sole inheritors of multiple evolutionary experiments that unfolded over millions of years. The living carriers of genetic and cultural adaptations accumulated across countless generations. This inheritance brings both privilege and responsibility. We benefit from adaptations developed by human lineages that no longer exist. We carry cultural knowledge refined through millennia of trial and error. And we alone determine how this legacy will shape Earth's future. The greatest mystery in our story isn't what happened in the past. It's what happens next. Having spread across the globe and transformed environments everywhere, having developed technologies that reshape the planet itself, having become the last human species on Earth, what will we become? Will we use our understanding of the past to create a more sustainable and just future? Will we recognize our shared inheritance and transcend artificial divisions? Will we preserve Earth's biodiversity rather than driving more species to extinction? These questions have no predetermined answers. They depend entirely on choices we make now. As we prepare to examine the remaining chapters of the Great Migration story, one truth stands clear: we were never truly alone. Our journey has always involved encounters with difference, different environments, different species, different ways of being human. How we navigate such differences may determine our fate. Chapter 8. Competing Pathways. As we've explored the Great Human Migration, several competing theories have emerged to explain how our ancestors populated the world. Each framework has supporting evidence and passionate advocates, yet each also faces significant challenges and contradictions. The truth likely contains elements from multiple models rather than a single perfect explanation. The traditional out-of-Africa model proposes a relatively straightforward narrative. Anatomically modern humans evolved in Africa around 300,000 years ago. After developing behavioral modernity around 70,000 years ago, a single successful migration left Africa around 60,000 years ago. These migrants eventually replaced all other human species without significant interbreeding. This classic model, dominant through the 1990s, emphasized replacement over assimilation. It suggested clean breaks between human species rather than complex interactions. Modern humans were portrayed as superior competitors who simply outperformed their archaic cousins through better technology, language, or social organization. The evidence supporting this model includes the relatively recent common ancestry of all non-African populations. Genetic studies consistently show greater diversity within Africa than outside it. This pattern aligns with what we'd expect if a small founding population left Africa and subsequently diversified as they spread globally. However, this straightforward narrative has been thoroughly complicated by recent discoveries. The extensive interbreeding with Neanderthals and Denisovans contradicts the pure replacement model. Fossil evidence suggests multiple migration attempts with varying success. The timeline appears more complex than a single exodus event. An alternative framework, the multiple dispersals model, proposes several successful migrations from Africa at different times. Early waves may have occurred during favorable climate periods around 120,000 years ago. These were followed by later migrations, including the major dispersal around 60,000 years ago. This model better accommodates archaeological evidence of early human presence in places like Israel, Arabia, and China. It explains apparently contradictory dating of sites without requiring implausibly rapid migration. It allows for complex patterns of population replacement, merging and coexistence in different regions. Genetic evidence offers some support for multiple dispersals, Some indigenous populations show unusual patterns of genetic diversity that might reflect admixture with earlier migrant groups. These genetic signatures could represent traces of earlier successful migrations that were largely, but not entirely, replaced by later waves. A third framework, the Southern Route hypothesis, emphasizes the importance of coastal migration. It proposes that the most successful human dispersal followed shorelines around the Indian Ocean. Marine resources allowed rapid movement without requiring complex adaptations to inland environments. This coastal highway facilitated the swift journey to Australia. This model explains the remarkably early dates for human arrival in Australia, at least 65,000 years ago. It accounts for the apparent speed of migration from Africa to Southeast Asia. It also explains why archaeological evidence along this route is limited. Many coastal sites would now be submerged due to rising sea levels since the Ice Age. For those who've been with us this far through this remarkable journey, I'm curious, which of these models seems most plausible to you based on the evidence we've explored? Share your thoughts in the comments below. Recent genetic studies lend some support to the coastal migration hypothesis. Indigenous populations along this southern route show genetic patterns consistent with relatively rapid movement. Their adaptations to marine environments and tropical climates suggest long association with these conditions. Their traditional skills often include sophisticated maritime technologies. However, the southern route can't explain all migration patterns. Human populations clearly moved inland as well, traversing mountains, deserts, and plains. The spread into Europe followed predominantly land routes. The peopling of the Americas required both coastal and interior pathways. No single route model can account for all the evidence. The leapfrog migration model offers yet another perspective. It suggests humans didn't expand continuously, but moved in punctuated jumps. Groups would migrate to favorable environments, bypassing less hospitable areas. Population growth in these refugia would eventually lead to further expansion when conditions permitted. This model explains the patchy distribution of early archaeological sites. It accommodates evidence that humans initially settled in environmentally favorable sweet spots rather than expanding uniformly. It also explains how populations could appear to leapfrog over apparently habitable territories. Climate fluctuations during the Ice Age provide context for this pattern. During harsh periods, populations would contract into refugia where conditions remained favorable. During warmer intervals, rapid expansion would occur as previously inhospitable territories became viable. This pulsed pattern of contraction and expansion shaped human distribution. Regarding interbreeding with other human species, two major models compete. The assimilation model proposes that archaic humans like Neanderthals were gradually absorbed into the expanding Homo sapiens population through interbreeding. They didn't so much go extinct as merge with our lineage. This model is supported by the significant archaic DNA in modern humans. All non-Africans carry Neanderthal genes. Many Asian and Oceanian populations carry Denisovan DNA. Some African groups show signs of interbreeding with yet other archaic human types. Genetic exchange clearly occurred repeatedly and significantly. The competing, mostly replacement model acknowledges interbreeding but emphasizes its limited extent. While hybridization occurred, the bulk of archaic populations were replaced rather than assimilated. The relatively small percentage of Neanderthal DNA in modern humans, 1 to 4%, suggests limited genetic exchange despite thousands of years of coexistence. This model points to the eventual disappearance of distinctive Neanderthal and Denisovan physical traits and cultural traditions. If true assimilation had occurred, we might expect more visible evidence of their physical characteristics in modern populations. Their complete disappearance as recognizable groups suggests replacement predominated over merging. The truth likely falls between these competing frameworks. Different patterns probably prevailed in different regions and times. In some areas, replacement may have been nearly complete. In others, significant assimilation may have occurred. The global pattern was complex rather than uniform. Regarding the causes of archaic human extinction, several competing theories exist. The competitive exclusion model suggests Homo sapiens simply outcompeted other human species through superior technology, cognition, or social organization. Our advantages gradually relegated other humans to marginal territories until they disappeared. This model is supported by the timing. Other human species vanished shortly after our arrival in their territories. It aligns with evidence that Neanderthal populations were already declining and fragmented before Homo sapiens arrived in Europe. Our presence may have delivered the final blow to already vulnerable populations. An alternative, the climatic stress model, emphasizes environmental factors. The extreme climate fluctuations of the late Pleistocene created challenging conditions for all human populations. Neanderthals and Denisovans may have been less capable of adapting to these rapid changes than our more culturally flexible species. This explanation is supported by evidence that Neanderthals were already retreating to southern refugia before significant contact with Homo sapiens. Climate reconstructions show increasingly harsh and unstable conditions during their final millennia. Their disappearance coincides with particularly severe climate oscillations. A third perspective, the disease exchange model, proposes that pathogens played a crucial role. When previously separated human populations met, they likely exchanged diseases to which the other group had no immunity. This pattern, well documented in more recent human history, may have devastated archaic human populations. While direct evidence for prehistoric disease exchange remains elusive, the model has theoretical support. Genetic studies show modern humans acquired some immune system genes from Neanderthals and Denisovans. This pattern suggests adaptation to novel pathogens was occurring. Disease exchange may have been a significant factor in these ancient encounters. As we approach the conclusion of our journey through human migration, these competing theories remind us that prehistory contains many possibilities. The evidence remains incomplete. New discoveries continually reshape our understanding. The full story of our ancestors' journey may be more complex than any single model can capture. Chapter 9. Breaking through the genetic time barrier. The last decade has witnessed a revolution in our ability to recover and analyze ancient DNA. Techniques once considered impossible have yielded genetic material from increasingly ancient specimens. This breakthrough has transformed our understanding of human evolution and migration. We can now peer directly into the genomes of our ancestors and their evolutionary cousins. In 2010, scientists announced they had sequenced the Neanderthal genome from bones over 40,000 years old. This achievement required overcoming enormous technical challenges. Ancient DNA is highly degraded, contaminated with bacterial material, and chemically damaged by millennia in the ground. Extracting useful genetic information seemed nearly impossible, yet through innovative methods, researchers isolated enough authentic Neanderthal DNA to reconstruct most of their genome. The results were shocking. Between 1 to 4% of the DNA in non-African humans comes from Neanderthals. Our ancestors had not simply replaced them, they had interbred with them. This discovery fundamentally changed our understanding of human evolution. The clean boundaries between human species blurred. Our lineage was not separate and distinct, but interwoven with those of other humans. The implications continue to reverberate through multiple scientific fields. Shortly after this breakthrough, analysis of a tiny finger bone from Denisova cave in Siberia revealed another surprise. The genetic material didn't match Homo sapiens, Neanderthals, or any known human species. A previously unknown type of human, now called Denisovans, had been identified solely through their DNA. Further genetic studies revealed Denisovan DNA in modern Melanesians, Australian Aboriginals, and some East Asian populations. Up to 6% of their genome comes from these mysterious humans. Yet we have only a handful of Denisovan fossils, a few teeth, a finger bone, and a jawbone. They are known primarily through their genetic legacy. In 2018, scientists identified something even more extraordinary, a direct hybrid. Analysis of a 90,000-year-old bone fragment from Denisova cave revealed an individual whose mother was Neanderthal and father was Denisovan. This young woman, nicknamed Denny, provided direct evidence of interbreeding between different human types. The identification of this first-generation hybrid confirms that different human species recognized each other as potential mates. These weren't rare, accidental encounters, but apparently deliberate pairings. The boundaries between human types were clearly more fluid than previously imagined. Our understanding of human species requires re-evaluation. More recently, genetic analysis has identified ghost populations, human groups that left no fossils, but whose genetic contributions persist in modern people. Indigenous West Africans carry DNA from an unknown archaic human that diverged from our lineage over 500,000 years ago. This phantom population interbred with the ancestors of modern Africans within the last 50,000 years. Similarly, genetic studies of indigenous Americans have found DNA segments that match neither Neanderthal nor Denisovan patterns. These likely come from yet another unknown human species. Our family tree continues to grow more complex as genetic analysis reveals previously invisible branches. This explosion of genetic information creates new paradoxes. If all these different human types could interbreed and produce fertile offspring, were they truly separate species? Traditional biological definitions of species emphasize reproductive isolation. Yet these ancient humans clearly weren't reproductively isolated from each other. Some researchers now suggest we should view Neanderthals, Denisovans, and perhaps other archaic humans as subspecies rather than distinct species. Others maintain that despite interbreeding, they remained mostly separate populations with different evolutionary trajectories. The very concept of species becomes blurred when examining closely related populations. Another paradox concerns the fate of archaic DNA in our genome. If interbreeding was significant, why do modern humans carry relatively small percentages of Neanderthal or Denisovan DNA? The answer appears to involve natural selection. Many archaic genes were selected against and gradually eliminated from our gene pool. Genetic studies reveal deserts of Neanderthal ancestry in regions of the human genome associated with male fertility. This pattern suggests hybrid males may have had reduced fertility. Such reproductive incompatibilities are common in the early stages of species divergence. They may explain why archaic DNA remains limited in modern humans despite significant interbreeding. However, some archaic genes were strongly selected for and remain common in certain populations. Tibetans possess Denisovan adaptations for high-altitude living. Some immune system genes of Neanderthal origin became widespread because they provided protection against pathogens. Natural selection preserved beneficial archaic DNA while eliminating harmful segments. This selective retention created another paradox: archaic DNA that helps some populations can harm others. Neanderthal genes that improved immune function in Ice Age Europe may contribute to autoimmune disorders in modern environments. Adaptations to ancient conditions can become maladaptations in our current world. Perhaps most puzzling is why some populations carry more archaic DNA than others. East Asians have slightly more Neanderthal ancestry than Europeans, despite Neanderthals being primarily European. Indigenous Australians and Melanesians have significant Denisovan ancestry, while mainland Asians have much less. These patterns don't simply reflect geographic proximity. Recent research suggests the answer involves multiple waves of migration and subsequent population mixing. The distribution of archaic DNA reflects complex demographic history rather than simple geography. As human populations moved, separated, and reconnected, they carried and exchanged various combinations of archaic genetic material. New analytical techniques allow scientists to determine when interbreeding events occurred. Neanderthal human interbreeding appears to have happened multiple times between 50,000 to 30,000 years ago. Denisovan interbreeding occurred at least twice with different Denisovan populations. These weren't single events, but recurring interactions over thousands of years. The timing creates another paradox. If significant interbreeding occurred over extended periods, why did these other human types disappear? Why didn't they simply merge with our species through continuous genetic exchange? What tipped the balance toward replacement rather than complete assimilation? Climatic data offers potential insights. The period between 40,000 and 30,000 years ago saw dramatic climate instability in Europe and Asia. These rapid fluctuations would have stressed all human populations. Groups with larger populations, wider geographic distribution, and more flexible cultural adaptations would have advantages during such volatile periods. Homo sapiens had spread across multiple continents by this time, creating a larger total population. This demographic advantage would have been significant during periods of local population crashes. When climate improved in affected regions, sapiens could recolonize from unaffected areas. Smaller, more isolated archaic populations lacked this buffering effect. Another paradox emerges from archaeological evidence of behavioral similarities. As contact between humans and Neanderthals increased, Neanderthal behavior appears to have become more modern. They began creating symbolic art, using body ornaments and adopting more complex technologies. Was this independent innovation or cultural borrowing from Homo sapiens? If Neanderthals could adopt complex behaviors from modern humans, why did they still disappear? Cultural transmission should have reduced any competitive advantages Homo sapiens possessed. Something beyond simple behavioral differences must explain the eventual replacement pattern. Demographic factors may have been more important than cognitive or technological differences. Recent archaeological discoveries continue complicating this picture. Cave art in Spain, dating to 65,000 years ago, precedes the arrival of Homo sapiens in the region. This suggests Neanderthals independently developed symbolic artistic expression. Similar findings of Neanderthal-made jewelry and pigment challenge assumptions about cognitive differences between human types. If Neanderthals possessed similar cognitive capabilities, including symbolic thinking and artistic expression, what fundamental differences remained? Were there subtle neurological distinctions not reflected in brain size? Differences in social organization or population structure? Or simply demographic and historical contingencies that favored our lineage? The most puzzling paradox may be why archaic humans disappeared completely as recognizable populations, yet their genes persist in us. If they were outcompeted due to inherent disadvantages, why would their genetic contributions be retained and sometimes favored by natural selection? This contradiction suggests the replacement narrative is too simplistic. New research exploring the functional effects of archaic DNA may hold answers. Neanderthal genes influence diverse traits in modern humans, from immune function to skin color, from pain sensitivity to mood disorders. These influences are complex, sometimes beneficial and sometimes detrimental depending on context. The genetic legacy of our cousins continues to shape us in profound ways. As genetic analysis techniques continue advancing, we may soon recover DNA from even older specimens. Researchers are exploring new methods to extract genetic material from fossils in environments where preservation is poor. The genetic time barrier continues to recede, potentially allowing us to peer further into our evolutionary past. These breakthroughs have revolutionized our understanding of human origins. Yet each new discovery seems to bring more questions than answers. The story of our emergence and dispersal across the planet grows more complex rather than simpler. We are approaching a more profound and nuanced understanding of what it means to be human. Chapter 10. We are all hybrids. Throughout this journey, we've been working toward a central revelation about human migration and evolution. The evidence now points to a conclusion that fundamentally changes how we understand ourselves. A truth that would have seemed impossible to scientists just a generation ago. We are all hybrids, mosaics of different human lineages combined into something new. For centuries, humans have drawn sharp distinctions between us and them. We've organized societies around perceived differences between groups. We've often treated these differences as fundamental and immutable. The science of human origins now thoroughly contradicts these divisive narratives. The boundaries between different human types were never as clear or impermeable as once believed. When our ancestors encountered other human species, Neanderthals, Denisovans, and others yet unnamed, they recognized them as potential mates. Genetic exchange occurred repeatedly over thousands of years and across multiple continents. This interbreeding wasn't trivial or insignificant. Up to 6% of the genome in some modern populations comes from archaic humans. These genetic contributions influenced crucial adaptations, from immune function to high-altitude tolerance, from skin pigmentation to fat metabolism. Our evolution has been shaped by these ancient exchanges. More remarkably, this pattern of genetic exchange extends throughout human evolution. Recent studies suggest even earlier interbreeding events between ancestral populations. The deeper we look, the more evidence we find of connections rather than separations. Human evolution resembles a network more than a tree. Even the concept of species becomes problematic when examining human evolution. If different human types could interbreed and produce fertile offspring, were they truly separate species? The biological species concept emphasizes reproductive isolation, yet these ancient humans clearly weren't reproductively isolated from each other. Perhaps most profound is the realization that our uniquely human traits may not be entirely our own. Some characteristics we consider fundamentally human might have originated in or been influenced by other human lineages. Through interbreeding, the innovations of multiple evolutionary experiments were combined. Neanderthals had larger brains than Homo sapiens. Their enlarged visual cortex may have given them superior spatial processing and night vision. When our lineages merged, did we incorporate cognitive elements from their neurological organization? Did their adaptations to European environments influence our brain function? Similarly, Denisovans had clearly developed adaptations for high-altitude living long before our ancestors attempted to settle such regions. Their genetic innovations for oxygen utilization now help Tibetans survive where lowlanders struggle. We didn't independently evolve all our adaptive traits, we incorporated some from our cousins. This hybrid nature doesn't make us less human. Rather, it expands what human truly means. Our species represents not the triumph of a single lineage, but the successful integration of multiple human experiments. We are the inheritors and carriers of diverse human adaptations and potentials. I'm fascinated by this revelation that we're all essentially hybrids. Does this change how you think about humanity's story? Share your thoughts in the comments. I'd love to know if this perspective shifts your view of our species' journey. This understanding fundamentally challenges racist ideologies that have sought pure lineages or superior populations. The actual story of human evolution involves continuous mixing, with beneficial adaptations spreading between populations. Genetic exchange, not isolation, characterizes our evolutionary success. Diversity became our greatest strength. The evidence also challenges traditional religious narratives that describe humans as separate from nature or specially created. We emerged gradually through evolutionary processes and share ancestry with other thinking beings. Yet this scientific understanding doesn't necessarily conflict with deeper spiritual meanings. It enriches them with a more complex truth. Our hybrid nature helps explain an enduring puzzle in human evolution. Homo sapiens evolved in Africa around 300,000 years ago, yet remained relatively unchanged for over 200,000 years. Then, within 50,000 years after beginning the Great Migration, we developed agriculture, cities, writing, and eventually industrial civilization. What triggered this acceleration? Perhaps it wasn't simply environmental challenges or random mutations. Perhaps it was the hybrid vigor that came from combining different human lineages. The merging of separate evolutionary experiments may have created cognitive and cultural possibilities that neither lineage possessed alone. Hybrid vigor, or heterosis, is well documented in biology. When previously separated populations interbreed, their offspring often show enhanced traits and adaptabilities. The combination of diverse genetic backgrounds can create novel genetic interactions with beneficial effects. Could our species' extraordinary adaptability stem partly from our hybrid origins? This hypothesis might explain why human technology and culture began accelerating after the migration from Africa. As our ancestors encountered and interbred with other human types, they incorporated not just their genes, but potentially their cognitive adaptations and cultural innovations. This hybridization may have catalyzed our extraordinary development. If true, this would mean our success as a species came not from replacing other humans, but from merging with them. Not from some inherent superiority, but from the novel combinations created through integration. Not from isolation and purity, but from connection and exchange. This reframes our entire understanding of human uniqueness. The implications extend beyond academic interest. If genetic and cultural exchange drove our success in the past, similar principles may apply to our future. Diversity and connection, not separation and homogeneity, may be crucial for continuing human flourishing. Our evolutionary history suggests isolation leads to stagnation, while exchange promotes innovation. This hybrid nature also suggests a different relationship with our extinct cousins. They are not simply failed experiments rendered obsolete by our superior adaptations. They are contributors to our genome, participants in our emergence. In a very real sense, they live on in us, their genetic innovations preserved in our cells. The evidence indicates these weren't simply isolated interbreeding events. Genetic analysis suggests repeated interactions over thousands of years across multiple regions. Different human populations experienced varying degrees of genetic exchange with archaic humans. The pattern was complex and ongoing, rather than rare and isolated. This extended period of interaction raises profound questions about the nature of these encounters. Were they peaceful exchanges or conflict situations? Were different human types recognized as people, albeit different kinds of people? Did they share language, cultural practices, or spiritual beliefs? The answers remain elusive. What we can say with certainty is that these encounters were significant enough to leave genetic traces that persist tens of thousands of years later. They weren't trivial or anomalous events, but part of the fundamental story of our emergence. We are their descendants as well as their replacements. The ultimate fate of these other human lineages as distinct populations remains debated. Climate changes, demographic patterns, competitive exclusion, disease exchange, and genetic absorption likely all played roles. The answer isn't simple replacement or assimilation, but a complex combination of factors that varied by region and time. What's clear is that within approximately 30,000 years of our ancestors expanding beyond Africa, no other human species remained as distinct populations. Yet their genetic contributions persisted within our lineage. They disappeared as separate groups, but continued as part of the emerging human whole. This pattern of hybridization didn't end with archaic humans. Throughout recorded history, human populations have separated, developed distinct characteristics, and later reconnected through migration and interbreeding. This cycle of divergence and convergence continues to shape human genetic and cultural diversity. The population of the Americas after 1492 represents this pattern at an accelerated pace. Indigenous American, European, African, and later Asian populations that had been separated for tens of thousands of years came together again. Their genetic and cultural recombination created new populations with novel characteristics. This process mirrors our deeper evolutionary past. Recent genetic studies confirm that this mixing continues and even accelerates in our globally connected world. Analysis of modern genomes shows increasing ancestry diversity within individuals. The future human population will likely show even greater integration of lineages that separated during the ancient migrations. We are reconnecting threads split tens of thousands of years ago. This perspective transforms how we understand human differences. The physical variations we observe between populations today represent relatively recent adaptations to different environments. Beneath these surface differences, we remain remarkably genetically similar, more so than almost any other widespread mammal species. Perhaps most profound is the implication for human identity. We are not simply Homo sapiens who replaced all other human types. We are a hybrid species, carrying genetic and potentially cognitive elements from multiple human lineages. We represent the integration of diverse human experiments into something new and uniquely adaptable. This hybrid vigor may be our greatest strength. The ability to incorporate beneficial adaptations from diverse sources, whether genetic or cultural, has characterized our species' extraordinary success. Our future may depend on maintaining this flexibility and openness to beneficial exchange, rather than seeking isolation or purity. As we face unprecedented global challenges, from climate change to emerging diseases, from resource limitations to technological disruptions, this understanding of our hybrid nature becomes increasingly relevant. Our success has always depended on adaptability through both biological and cultural means. Our hybrid origins may be the key to our future resilience. The story of human migration and evolution doesn't end with our current understanding. New discoveries continually reshape the narrative. Technologies for analyzing ancient DNA, dating archaeological sites, and reconstructing past environments continue advancing. Each breakthrough brings us closer to understanding our complex origins. Perhaps the most remarkable aspect of this story is that it's fundamentally about connection rather than separation. For generations, humans have emphasized differences between groups, differences in appearance, language, belief, and culture. The scientific evidence reveals these differences as superficial compared to our profound shared heritage. We now know that all humans alive today share ancestors who lived just a few thousand years ago. We know that beneficial adaptations have spread between populations throughout our evolution. We know that our lineage incorporated genetic material from other human types. Connection and exchange, not isolation, define our story. This understanding doesn't erase human diversity. It contextualizes and celebrates it. The variations between populations represent successful adaptations to different environments and historical circumstances. They demonstrate our species' remarkable flexibility rather than fundamental separations. Diversity becomes our strength rather than a basis for division. As we look toward humanity's future, our evolutionary past offers crucial insights. Our success has always come from adaptability, both biological and cultural. Our willingness to exchange beneficial innovations across group boundaries. Our ability to incorporate diverse perspectives and approaches into new syntheses. The challenges we face in coming centuries will test these adaptive capacities as never before. Climate change, resource limitations, technological disruptions, and other global issues require unprecedented cooperation. Understanding our shared origins and hybrid nature may help foster the connectivity needed to address these challenges. In the end, the story of human migration reveals something profound about our species. We are all descendants of restless explorers who ventured into the unknown, all carriers of adaptations refined across diverse environments, all inheritors of multiple human lineages whose innovations live on in our bodies and cultures. The journey that began 60,000 years ago continues today. We still migrate, adapt, and exchange genes and ideas across populations. We still face environmental challenges that test our flexibility and resilience. We still carry the legacy of those ancient pioneers who first ventured beyond familiar horizons. If this exploration of humanity's remarkable journey has sparked your curiosity about our ancient past, consider subscribing to our channel. Each episode uncovers another chapter in the extraordinary story of how we became who we are today. What other mysteries of human history would you like us to explore next?